Students, today we are going to discuss about graph theory. Introduction. What is a graph G? It is pair G equal to set of V comma E, where V equal to V of G, that is equal to set of vertices. E equal to E of G, that is set of edges. For example, V equal to S comma U comma V comma W X Y Z. These are all vertices. E equal to X comma S, X comma V, X comma U, V comma W and so on. These are all edges. Vertices denoted by point. That is X, V, W, Y, Z, U. These are all vertices. It is marked by a simple dot. Then edges. Two vertices connected by a line or path, that is an edge. That's all. In simple, two vertices connected by a line, that is edge. Next, edges. An edge may be labeled by a pair of vertices. For instance, E equal to V comma W. V comma W joined by a line, that is an edge E. E is said to be incident on V and W. Next, isolated vertex. A vertex without incident edges, that is single dot, without incident edges, that is called isolated vertex. Next, special edges. First one, parallel edges. Two or more edges joining a pair of vertices. For example, A and B are joined by two parallel edges, that is parallel edges. A and B joined by a line and also joined by a curve. These two are parallel edges. Next definition, loops. An edge that starts and ends at the same vertex. In the vertex D, example, in the vertex D, an edge started from D and end also in D. So that is called a loop. So an edge that starts and ends at the same vertex, that is called a loop. Next, special graphs. First one, simple graph. A graph without loops or parallel edges. A graph without loops or parallel edges is called simple graph. Next definition, weighted graph. A graph where each edge is assigned a numerical label or weight. Suppose an edge assigned by a number, that is called weight of that graph. Next, directed graph, other name digraph. G is a directed graph or digraph if each edge has been associated with an ordered pair of vertices. Each edge associated with an ordered pair of vertices. That is, each edge has a direction. This is called digraph. Next concept, complete graph Kn. Let n greater than or equal to 3. N value must be greater than or equal to 3. The complete graph K is the graph with n vertices and every pair of vertices joined by an edge. Okay, complete graph K1 is the graph with n vertices and every pair of vertices joined by an edge. The figure represents K5 because here we have 5 vertices. So n vertices, therefore complete graph K5. Here every pair of vertices joined by an edge. Next, connected graph. A graph is connected if every pair of vertices can be connected by a path. Okay, connected means every pair of vertices must be connected by a line or path. That is connected graph. Each connected subgraph of a non-connected graph G is called a component of G. Suppose in a connected graph, we should select some parts only, but without connected. That part called component. Next, adjacency matrices. Definition. Aij equal to 1, 0. It has two values 1 and 0. If Vi Vj has an edge means that value 1, otherwise 0. In that figure, just listen. Here we have 4 vertices A, B, C, D. Okay. Now A to A there is no connection. That is, there is no loop. Therefore, first value in that matrix, first value A11 value 0 because there is no loop in that vertex A. Next vertex B. Here A to B there is a path, there is an edge A to B. So in that matrix first row second value 1, A to B value 1. Next A to C there is an edge between A and C. So third value also 1. A to D there is an edge between A and D. Therefore fourth value, first row fourth value 1. So first row over. Similarly second row B to A there is a path between B to A. Therefore that value 1. B to B there is no loop. So that value 0. B to C there is an edge. So that value 1. Next B to D there is no edge between B to D. Therefore that value, last value, second row last value 0. Similarly third row C to A there is a path. Therefore that value 1. C to B there is a path. Therefore that value 1. Next C to C there is no loop. So that value 0. C to D also there is no connection between C to D. Therefore that value also 0. Fourth row D to A there is a path between D to A. There is an edge. Therefore that value, fourth row first value 1. Similarly D to B there is no edge. D to C there is no edge. D to D there is no loop. So remaining values will be 0. This is adjacency matrix. Next definition, next concept, incident matrix. Here we chose that matrix. Label rows with vertices. Label columns with edges. Columns denoted by edges. 1 if an edge is incident to a vertex. Otherwise 0. If an edge is incident to a vertex means that value 1. Otherwise 0. First they are choosing V, W, X, Y are vertices. V, W, X, Y are vertices. E, F, G, H, J are edges. First V to E. First value V to E. E edge incident with the vertex V. Therefore that value 1. Next edge F. F incident with V. Therefore that value 1. F next G. G not incident with V. And also there is no connection between V and G. That value 0. Similarly there is no connection between V and H. So that value also 0. Similarly there is no connection between V and J. See that figure. V and J there is no connection. So that value also 0. Next W. W to E. W to E. E incident on W. So that value 1. Next F doesn't incident on W. So that value 0. Next W to G. So G, edge G incident on W. Therefore that value 1. Next H doesn't incident on W. So 0. Then W to J. W to J. So there is an incident. J incident on W. So that value 1. Similarly, we should check remaining 2 rows. Okay, this is incidence matrix. By using this figure, we are going to formulate this matrix. Okay. Next, here one example. Draw a graph with the adjacency matrix. A, B, C, D, 4 vertices. In this graph, we are going to write a sample matrix A, B, C, D. In row A, B, C, D, column A, B, C, D. We should write adjacency matrix. First A to A 0. A to B there is an edge. So that value 1. Next A to C value 1. A to D there is no direct connection, so that value 0. Similarly B to B no connection, so 0. Next B to A there is an edge, so that value 1. Next B to C there is no connection, so that value 0. B to D there is an edge, so that value 1. Similarly we should check C and D vertices. Try yourself and form a matrix. Next definition, paths and cycles. Very simple one. A path of length n is a sequence of n plus 1 vertices and n consecutive edges. Path of length n, that is n number of length and n plus 1 vertices. Here in the first figure 1, 2, 3, 4, 5, 6, 7. There are 7 edges, but vertices 8. That is n plus 1 vertices. N edges and n plus 1 vertices. That is n consecutive edges. That is the path. There is no break between that edges. Next cycle. A cycle is a path that begins and ends at the same vertex. Okay. Suppose we start from A means it should end on that A vertex. That is the cycle. Okay. Next Euler cycle. An Euler cycle in a graph G is a simple cycle that passes through every edge of G only once. That is Euler cycle. That passes through every edge of G only once. Next concept, degree of a vertex. Degree of a vertex V denoted by del of V or d of V. That is number of edges incident on V. Number of edges incident on every vertex. Suppose a vertex A. Number of edges incident on A are 1, 2, 3, 4. In this diagram, 4 edges incident on A. Similarly, for the vertex B, 3 edges incident on B. Similarly, for E, 4 edges incident on E. So, degree of E equal to 4. Degree of A equal to 4. Degree of B equal to 3. Similarly, degree of D. What is degree of D? In the vertex D, 1, 2, 3, 4, 5, 6 edges incident on D. Therefore, degree of D equal to 6. Similarly, we should check remaining vertices. Okay. Next one concept, sum of the degrees of graph. If G is a graph with m edges and n vertices v1 to vn, then sum of degree of vertices equal to twice the number of edges. That is summation d of v equal to 2m. Del of v equal summation del of v equal to 2m. Sum of degree of vertices in a graph, sum of degree of vertices equal to twice number of edges. This is one of the theorem, very important one. Next, Hamiltonian cycles problem. That is a traveling salesperson problem. This is based on Hamiltonian cycles. First concept, to visit every vertex of a graph G only once by a simple cycle. Visit every vertex only once. In Euler cycle, visit every edges only once. In Hamiltonian cycle, visit every vertex only once. Such a cycle is called a Hamiltonian cycle. If a connected graph G has a Hamiltonian cycle, then G is called a Hamiltonian graph. This is example of non-Hamiltonian graph. We can't visit every vertex only once. Therefore, this graph is called a non-Hamiltonian graph. This is some examples for Hamiltonian circuit and Hamiltonian path. G1 Hamiltonian circuit. G2 there is no Hamiltonian circuit. And G3 neither Hamiltonian circuit nor Hamiltonian path. Thank you.